configuration and weight estimation. Our today's lecture is dedicated to the stability of aircraft. Uh, but before that, sorry, but before that, uh, we will go through some basic topics like center of pressure and aerodynamic center, relation between 2 points and neutral points, and why the tail is important to increase the stability. Okay, and in the end of this presentation, you will be actually able to select various component of aircraft for making any like RC plane or glider or something. And in the end of this webinar, we have a short demo of aircraft uh, stability using XFLR5. So stay tuned for that. And also, okay. So let's start. First topic is center of pressure. So as we all know, as we all familiar, how the pressure distribution around an airfoil look like. So it is obvious that there is a some point exists some point where the resultant force acting, right? So this point is known as center of pressure, and another definition is it is the average location of a pressure over a wall airfoil. Okay, so as you can see in this figure, the airfoil is situated at an angle, some angle alpha, and the lift and one second, lift and drag acting at this point, which is a center of pressure. Okay, and the moment the as a lift and drag uh, acting at this point, so there is a no moment about this point, right? So moment means torque, like the torque about this point is zero, right? But the thing is, suppose the airfoil situated at an angle 10 degrees and another same airfoil situated at an angle 13 degrees. So as you can see, the pressure distribution around an airfoil changed, right? So obviously the position of a center of pressure is changed, right? So the center of pressure move with the angle of attack. So it's not a static point. So this creates some issues with engineers and scientists, who are trying to formulate this in his theories and try to do some simulation in his CFD softwares. So basically, it is very difficult to take it as a reference for aircraft analysis. So now it is a very difficult. So what we do, we will try to form one point. It's an assumed point which will not move but still capture our physics of aircraft. So that's why the aerodynamic center come into the picture. Now in this picture, the lift is actually acting on a center of pressure. But is it true? No, right? Because the lift is, as we learned that the lift is acting on a center of pressure. So uh, So if we want to move the position of force, then we have to apply the associated moment at that point. So let's verify this fact that suppose the force is acting, suppose this is a rod and this is a hinge point of the rod, and the force is acting at a distance 2r from this hinge. Now we want to take this force and supply at the middle, and uh, so what happened? We have to apply associated moment with magnitude F into R at here at a middle point, right? And another beauty of this aerodynamic center is this moment, this pitching moment is also remain constant. So as the this is also actually definition of aircraft. So it is a point where the pitching moment coefficient, so this moment is remain constant with angle of attack, means it's not changed with angle of attack or a lift coefficient. Okay, and obviously this is a not change with angle of attack. This point is not changed. The position of this aerodynamic center is not changed with the angle of attack, and so that we can take it as a reference point. And generally, for a low speed aircraft and uh, thin airfoil, it is nearly at a C by 4. Okay, now we are going to do some mathematical derivation, like for finding center position of center of pressure and aerodynamic center. So let's find the relation between the two moment coefficient. So first moment coefficient is ma, where A is a distance between this point and this point from the leading edge. And the same airfoil with the same angle of attack, another moment is mx with a distance x from the leading edge, right? Now, before we proceed, this will keep it in mind that this is, you need to keep it in mind that the nose up moment is positive and nose down moment is negative. Okay, so for this diagram, uh, the moment about a leading edge can be write like this. So moment about leading edge MLE is equal to moment about point A, because this is a nose up moment, so that's why we take a positive sign here. And the moment about the moment to by this like L cos alpha plus D sin alpha is a nose down moment, so that's why we take a negative sign here, this and this. Now for this diagram, the moment about leading edge can be write like similar way, right? And now the both is the same airfoil and at the same angle of attack, so moment about leading edge it's remain same, like, so we can equate this to equation, and we can do some mathematical manipulation and we get this equation, like, sorry, this equation where CMAC is a moment about aerodynamic center, CMA is a moment about point A. A can be any point, like it can be leading edge, it can be trailing edge, it can be quarter chord point of the airfoil. Okay, and CL is a lift coefficient, and A, as you will know, it is a random point, and C bar, this C bar is a chord, like mean aerodynamic chord. Okay, now uh, we know that moment about aerodynamic center is remain constant, right? So with respect to alpha and with respect to CL, so we can, if differentiate with respect to alpha, then we get 0, right? Obviously. So after the place this differentiate upper equation, we get this equation, like where x AC is a point position of aerodynamic center from the leading edge, and A can be any point, and this term is a derivation of a moment about the point A with respect to CL. Okay, so this formula is important, and please keep it in mind that. Okay, now for a center of pressure, we replace any position, we replace like any random point by center of pressure, right? So we replace A with a position of center of pressure from the leading edge, and we know that the moment about the center of pressure is 0. Okay, so we put this equation and we do some mathematical step and we derive this equation. We take alpha small and we get this equation where xcp is a position of center of pressure, and c bar is a, as usually, mean aerodynamic force. Cl is a lift coefficient, and cmac, the sign of a cmac is actually depend on the relative position of a cp and ac. Okay, so let's verify this formula. Suppose the airfoil is situated at an angle alpha and the lift and drag acting center of pressure, and suppose the aerodynamic center ahead of cp, and now we take this drag and supply it aerodynamic center, and we take this lift and supply it here. Now we get this, and so if we move the position of force, then we have to apply moment, right? So we have to apply nose down moment at aerodynamic center for keep this both scenario same, right? So we apply nose down moment, so value of the sign of cmac is negative, right? So we get negative negative positive, and we get the value of xcp more than xac. So as we can verify from this diagram. Okay, so this is formula, you need to remember, like something like that. And let's do some, let's see some properties of center of pressure in aerodynamic center. So first property is, so in this equation, if we put the moment about aerodynamic center 0, then what we will get, xcp is equal to xac, right? So the moment about aerodynamic center is 0, then these 2 points is coincide. Okay, and the second property is, for a symmetrical airfoil, the center of pressure is lies closely to the 25% of the chord length from the leading edge. Okay. And the third point is, if we increase the angle of attack, so that the position of center of pressure change, but in which direction it moves forward. Okay, so keep it in mind, and you can verify from this diagram. And this is a summary of formula which we derived in earlier previous slide. Okay, so now the important topic of today's webinar is stability. So the simple definition of a stability is, we know that it is the ability of a aircraft to withstand with any disturbance and continue its normal flight. So the classification of the stability we will cover in the GitHub material. The first is static stability, second is dynamic stability, and the static stability is the initial response of aircraft, and further classify into positive, negative, and neutral stability, static stability. And the dynamic stability is a response of aircraft after a certain time, and it can be also classified into the plausible, same as the static stability, right? Positive, negative, and neutral. And this is the diagram. This is a photo of like dynamic stability. So as you can see, if the amplitude remains same, this is a neutral. If amplitude decrease, then this is a positive. If amplitude increase, then it is negative static dynamic stability. Yes, anyone?
Umesh, you can pause in between if anyone has any doubt. You can take that over.
Okay. So okay, okay. So if you, I urge you to, if you urge you to unmute or type in chat if you have any doubts. Okay. So let's move forward. Another topic is, uh, now we are going to see the CM versus angle of attack curve and how it is effect to the stability of aircraft. So in this diagram, in this curve, CM versus angle of attack, which I have shown you in the first webinar. This graph is for three different aircraft. For a stable aircraft, the slope of the curve is negative. For a neutral stability, the slope of the curve is 0, and for a, sorry for that. Okay, sorry for that. So yeah, I hope you understand this, like this CM versus alpha curve. And actually, 1 second, sorry for that. Just 1 second. Okay, so uh, hmm, so this is covered. So and also I have told you in the first webinar, like that how the we can find the stability using this graph, right? And actually, in this in the end of this webinar, we will actually see like how the center of gravity affect this slope of this CM versus angle of attack curve. Okay, so stay tuned for that. Okay, and the next is another topic is neutral point. So it is, so uh, all you understand, no? See what is like how the stability effect with CM versus angle of attack curve by. Okay, so I hope you understand. The next is neutral point. So it is just a critical location of a center of gravity. Now listen, the center of gravity is a totally depend on a weight distribution of an aircraft, right? And it is in our hand, right? Which means that we can change the position of center of pressure where we want. And now what is a neutral point? It is neutral point is that location of center of gravity for which the aircraft become a like neutrally stable. Statically neutral means, which means that dcm by d alpha 0. And the point which need to remember is, if the the position of a center of gravity is ahead of a neutral point, then it is a statically stable, and if it is behind that, then it is unstable. Now it is about a neutral point, and in this figure, the static margin, the new term is static margin, and it is depends on the difference between these 2 points, like center of gravity and a neutral point. And uh, like formula for static margin is look like this. And what is actually in other words, the uh, static margin is a slope of the curve CL versus CL curve. Okay, so this is a information you need to remember. So this, I hope it's clear. So now learn more about a neutral point with the help of this longitudinal static stability. So in this diagram, if you want to write the moment about CG, then we can write this equation, right? Like am moment about the center of gravity is equal to moment about aerodynamic center, which is nose up, so that we can take positive, and uh, like and this is like moment due to this lift is nose down, right? So that's why we take a negative sign here. And now what we will do, we divide this equation by reference moment. The reference moment is half rho v square into area into mean aerodynamic chord. So C bar is mean aerodynamic chord here. And we differentiate with respect to alpha. Then as we know that for a stable flight, for a stable aircraft, this dcm by d alpha value is negative, right? So one negative is already here, and that's why this need to be positive, right? So so from that we get this inequality, this relation, that the position of aerodynamic center should be behind the center of gravity. So that's exactly written in this line. Okay, for this wing only configuration, you have to select a position of a center of gravity ahead of aerodynamic center. Okay, now the neutral point for a wing only configuration. What is a neutral point? Neutral point is that position of a CG where the aircraft is neutrally stable, right? So as we know, for a neutrally stable, what is the condition of neutrally stable? dcm by d alpha is 0, right? So that means we get the xac is equal to xcg. So, and we know that the neutral point is just a location, like location of CG, right? But the location of CG is actually aerodynamic center. So that's why for a wing only configuration, the aerodynamic center is actually coincide with a neutral point. So this is for only wing only configuration, not for all aircraft. So please keep in mind. Okay. So if you have any doubts in this or any previous slides, so you can ask, or if not, then we will move ahead. Okay. Okay. So now we will learn about importance of tail and how to manufacture aircraft. So Akshat will take over that part. So please Akshat,
Yeah, I'll just share my screen.
one second. I will unshare my screen. Okay, you can share.
Is it visible?
Yes,
Yes,
it's visible.
Akshat. Yes.
Okay. So right now we have understood that for a wing only configuration, just yeah, so we have understood that for a wing only configuration, our neutral point coincides with our aerodynamic center, right? So for having a stable wing only configuration, it looks like what we just need is that we adjust our CG like this, that the CG lies ahead of the aerodynamic center, and we will get the whole stability thing, that we will get a stable flight for our aircraft. But are these things that simple? So everything looks good, but no, that is not the case. So can anyone here unmute and tell me what will be the problem, that even if we are giving us our aircraft the stability, it will still not have a good flight? So what can be the reason behind it? Can anyone unmute and tell it? Okay, no problem. So I'll go ahead. So as in the previous slide, you saw that about the center of gravity, if we write our moment, it comes out to be MAC minus lift, that is L, into XAC minus XCG. So this looks good, but let us examine the equilibrium condition. So what happens at equilibrium condition is the moment about center of gravity will reduce to zero. That is the definition of equilibrium condition, right? So by that we get MAC is equal to L into XAC minus XCG. So what happens after that is MAC, as you know, that for a stable aircraft, we have MAC as inherently negative. And we just saw in the previous slide that for stability, we need to adjust our center of gravity as such that it lies ahead of the aerodynamic center. So this quantity will be a positive quantity. So can you now see what will be the issue, that this is a negative quantity and this is a positive quantity and this is a lift. So what will be the issue that this aircraft will face at the equilibrium position, considering the wing only, considering the wing only considering the wing only configuration for our aircraft? So can now you infer from this equation that what will be the issue for such an aircraft which just has wing? Yeah, can anybody tell that? All right, so as you can see here in this equation, this term is negative and this term is inherently positive. So this lift term will become negative, and boom, what happens when lift becomes negative? Your aircraft will no longer fly, right? So this is a major issue, that your lift at equilibrium position is coming out to be negative. So that is not what we want. So this will create a huge problem for our aircraft and it will not be able to fly considering the equilibrium condition, right? So what can be the solution for this? So if you examine this equation, if we can adjust our CG such that it goes beyond AC, then this term will become negative and this is inherently negative, so we will get a positive lift at equilibrium condition too. But can we do that? So here's a caution, that we can't do this in a wing only configuration, because we just saw that the neutral point and aerodynamic center for our wing coincides. So if we take our CG beyond aerodynamic center, it will automatically go beyond neutral point too, and that will affect its stability. It will no longer be statically stable. So we can't do that. So we need to devise a way which allows us to move our center of gravity away, beyond our aerodynamic center, so that we can get a stable flight as well as a positive lift at equilibrium condition. So what can be the solution for that? So let us examine that, does a tail help? We have seen many aircrafts and we have seen that they use tail, so there must be some reason for it, right? So what is the exact reason? So does having a tail help the aircraft resolving this situation? So let's start with more basic approach to understand this, and let's have a look on the schematic of our aircraft. So let's suppose that this is the fuselage reference line of your aircraft and these are the wing and tail. That is the side view of wing and tail. And these are set at a particular angle with respect to the fuselage reference line, that is called the wing setting angle and tail setting angle respectively. This is the free stream velocity of your aircraft. Like this is the free stream velocity of air at the wing position. And what happens at the tail, the free stream velocity will not longer be the actual velocity of air at the tail because of downwash. As we studied in the first webinar, there happens downwash which provides the velocity, downward component of velocity near tail. So this will make your actual velocity at tail to be somewhat different from the free stream velocity, and that becomes v dash. And the angle between these two velocities is termed as the downwash angle, a measure of the finite wing downwash, which we studied in the first webinar, right? So these are the fuselage reference line angle of attacks, and this is the location of your CG, let's assume. So what we need to write here is we need to look at the angle of attack for our tail. So let's look at the angle of attack for our tail. So angle of attack for your tail comes out to be this. And how does it come out? So as you can see that alpha for wing will be IW plus alpha FRL, right? So your alpha FRL can be written as alpha W minus IW. And if you look at the angle of attack at your tail, so it will come out to be IT plus alpha FRL and minus epsilon due to this downwash. So finally your angle of attack at the tail position will come out to be alpha W minus IW minus epsilon plus IT. So this is the schematic of your aircraft, which is also having a tail along with a wing, and this is the value of angle of attack at the tail. Let's move forward. So what happens at this tail is, so now this V dash is the actual velocity of free stream at your tail. So perpendicular to it will be a generated lift at tail, and parallel to it will be a drag generated due to lift. And these angles, as you can see by geometry, will be alpha FRL minus epsilon. So if anybody has any doubts in these diagrams, like how we are getting the lift and particular drag positions or directions, so you can unmute and ask now. Okay, so I presume no doubt. So let's move ahead. And yeah, this distance from your CG and the tail, that is more precisely the aerodynamic center of your tail and CG. This distance is termed as tail moment arm and is represented by LT. We'll look how it helps us in writing the moment. So if we write the moment about the center of gravity just due to the tail, like we have seen previously the moment about center of gravity due to wing, right? So let's now examine what tail contributes to the moment about center of gravity. So if you write the expression for moment about center of gravity for the tail, it comes out to be this quantity, and this is the moment about aerodynamic center of tail, and it's a small quantity, so we'll neglect it in further approximations. So, and this term comes out to be as it is, like it is the moments due to the perpendicular components of lift as well as drag, that is LT cos this angle and dt sine of this angle. So for our considerations, we consider smaller angle of attack. So this angle term goes to 0. So what we finally get from our assumptions is that the moment due to tail which we get is minus LT into capital T. That is the tail moment arm multiplied by the lift generated at tail in a negative direction, right? If we consider this in the coefficient form, we get this. So a point to remember here is that while you are converting your moment to the coefficient form, you use the free stream velocity, that is the free stream dynamic pressure, which was actually hitting the wing, and while writing the lift at the tail, you will take up the velocity which is at the tail, that is V dash. So here is where the effect of downwash comes into play. So substituting this lift expression as well, you get this quantity, and these look so heavy, so we don't use them directly. So we take them up, we club them together into certain coefficients, and let's see how those coefficients are clubbed together. So this particular term, that is LTST upon C bar S, that is the tail moment arm, area of tail, and the area of wing and mean aerodynamic chord. This whole terms comes into this coefficient that is called VH, and this is also known as the tail volume ratio. So what is the importance of this tail volume ratio? It later helps us in determining the size of our tail, right? You can see here that there is a term for area of tail in its expression. So this will help you in determining the size of your tail. And this eta term is referred to as the ratio of dynamic pressures at tail and the free stream. That is basically half rho v square at tail, that is due to this v dash, and half rho v square, that is of the free stream. So if anybody has any doubt in these coefficients, definitions or their representations, you can unmute and ask now. Okay, so as you can see, these all are mathematical manipulations. So we are just focusing on the final results here. Let's move forward. Yeah, so as you can see from the last slide, like this CMT, so these are two coefficients which we will get values from historical data or something, or some external source. But what we need for our aircraft, which will be unique for our aircraft, will be this CLT, right? So to get the whole contribution of our tail in the moment, we need the contribution of tail in the lift, right? That is the CLT. So let's look how we get the CLT. So as from the previous knowledge from first webinar, as we discussed, like we can write the CLT as CL alpha T into alpha T, where CL alpha is the slope of the graph between CL and alpha curve, and alpha T is the angle of attack at the tail. So as we looked initially, that angle of attack at the tail can be written as like this. So you get the expression for CLT as follows. Also, you get some expression for downwash angle, which also depends on the angle of attack at wing, that is alpha W, and this can be written as this quantity. So keep calm that it's just math, and you don't need to remember all these formulas. We just want you to get an understanding of how tail is helping in stability, so we are showing you all the mathematical manipulations, because when you see the math, you get more trust of anything being told, right? So some more mathematical equations coming your way, so beware of that. So if you substitute this CLT value in the previous equation of CMT which you got, so this will come out to be this, and clubbing these particular coefficients together, that is the clubbing the terms dependent on alpha of wing together and the constant term, you can get the two main components for that the two main factors which are important to understand the contribution of tail in your actual torque, that is in your whole moment. So this Cm naught T will come out to be this, that is the constant term in this equation, and this Cm alpha T will come out to be this, that is the coefficient of this alpha wing, that can also be looked at as the slope between Cm and alpha W curve. So yeah, so in this way we have got all information about our tail, right? So like whenever we want to understand the contributions of any component in our aircraft, we will look at these two parts, that is Cm naught for that part and the Cm alpha. So as you can see that we have got these two components for our tail, so now we can now say that we have understood all the contribution of tail in our moment. So let's look how it helps us. Now let us look at the aircraft as a whole. So all those equations which we have done till now were just dependent on were just considered for the tail. So now let's look at the aircraft as a whole, and what we mean by aircraft here is that is the contribution from wing plus the contribution from tail. So if you write Cm naught for whole aircraft, it will be Cm naught for wing plus Cm naught for tail. Also, if you write Cm alpha for both the parts, so you will get Cm alpha wing plus Cm alpha tail. And now putting the appropriate values for wing and tail, which we discussed previously, we get this whole quantity. So yeah, so we have done many mathematical manipulations in the way to get this formula, but what is the use of it? Like, what does our aircraft gain from it? So this is the situation we move from. This is the situation we started from, and finally this will be the situation we get here. So this aircraft, as you can say that it is written here that get a tail, get a flight. So tail is that important that it is crucial for your flight. This aircraft didn't have any tail, so it lost its lift at equilibrium position, as you saw earlier that the lift was negative. But now this aircraft will not face that situation because it has a particular tail. So can you tell me how the tail is affecting this particular quantity, like how the tail is affecting this negative lift anomaly that we were getting in the wing only configuration? Why are we not facing that problem in an aircraft which has tail? So can anybody unmute and just tell me what we have achieved from giving our aircraft a tail? I want you to focus on this equation and you can actually get the answer. if you focus on this equation. Remember the neutral point and all those things. The main reason was that for a wing only configuration, we were not allowed to move our center of gravity beyond aerodynamic center. So can we do that thing looking at this equation? Can you infer that we can do that? Yeah, okay, no problem. So as I was saying that look up at the neutral point. So the main issue for your wing only configuration was that your neutral point was coinciding with the aerodynamic center, and that is why you were facing a negative lift in all stable conditions at the equilibrium position. Now you don't, yeah, so now you will not face that equation, and let's see why is that the case. So as Cm alpha is 0 for neutral point, that is the definition of neutral point. Yeah, so by keeping Cm alpha 0 in that previous equation, we get this quantity. So if you manipulate it properly, so you get the value of your neutral point, and focus here that your value of neutral point for you comes out to be greater than the aerodynamic center, right? Here that is a positive quantity, and the neutral point is aerodynamic center plus something. So basically your aerodynamic center is now behind the neutral point. That means the neutral point has shifted ahead of the aerodynamic center. So your CG is happy now, like it says I'm free now. So why is it free? CG can now go beyond aerodynamic center up to the new neutral point for a stable flight. As you can think here that aerodynamic center is somewhat here and neutral point is somewhat here, let's say. So your CG can lie anywhere between those 2 points, because the only condition for your flight to be stable was that your CG must lie ahead of the neutral point. And if you can achieve that, you will get a stable flight. Also the anomaly of negative lift at equilibrium can be solved now, because what was the reason for that negative lift anomaly? It was that you were not allowed to take your CG beyond aerodynamic center, and now that you can do that, you will get a stable as well as a positive lift at equilibrium condition. So that will give you a great flight, and that will make the aircraft successful at all conditions of stability as well as equilibrium. Yeah, so here we conclude the stability part, and now we'll move ahead for the design part. That is all those things which we have learned so far, we will club them together and see how they will help us in actually manufacturing a real aircraft. So as we discussed in the previous webinar, we discussed about the weight iteration method, and we had got the total weight of our aircraft as well as the different components of it. So here is a parameter which we use now, that is called wing loading. And what wing loading is defined as? It is defined as the weight of whole aircraft divided by the area of wing. So here somewhat we are assuming that the whole wing has to carry the whole weight of our aircraft, that it has to support the whole weight of our aircraft. So wing loading is something that is the weight. Wing loading is something which helps us design our wing. So that is defined as the weight of total aircraft divided by the area of wing. Now generally we have the wing loading value for our aircrafts as 50 gram per centimeter square, and we'll look how it helps us. So yeah, so we had the weight of our aircraft, and through wing loading we can get the area of our wing. So we can actually start designing our wing from that. So through weight we have got the wing area now. Also, so we have the area wing now. Also about the aspect ratio. Aspect ratio is generally taken between the values of 6 to 8. So having got the area of wing and the aspect ratio, you can now get the wingspan, because aspect ratio is defined as wingspan square divided by the area, and thus you get the wingspan for your aircraft. So what you have got almost all conditions for your wing, that is the wing area, wingspan, wing loading, and all those. So generally the length of the fuselage. Yeah, so now let's look at the fuselage. So fuselage is generally almost 80% of the wingspan. It's a historical data which most of the aircrafts follow. So we can safely assume that to be true, and we can take the length of our fuselage to be around 80% of the total wingspan of our aircraft. So from this we have got the weight of total aircraft, we have got the information about our wing, and we have also got the information about our fuselage. So now remains the tail. So as you can remember that previously we saw at the tail volume ratio, we saw the tail volume ratio, which I said that will help us in actually determining the size of our tail. So VH, as you can remember, that it was giving us the size, that is the area of our tail. So we now also have information about our tail. So now what remains is so for our aircraft to operate, we need to choose a CL value according to our mission requirements, and that is called the design CL. So we can't just keep changing our CL values during our mission. So we take up a particular CL value that we call as a design CL, and we design our whole aircraft on the basis of that. And how do we get that? So as you can remember from the cruise equations, we had in the cruise equations, the weight is equal to lift, and writing the expression of lift here, you get CL value as this. So what are these components here? So you can see that W by S, this is the wing loading which we saw in the previous slide, and rho is the function of your altitude at which you are flying, and V is the velocity of your cruise flight, which is mostly given as a mission requirement. So in this way you get the design CL for your aircraft. So why do we get this design CL? So how are we going to help? How are we going to get help from this design CL? So this helps us in choosing the airfoil for our aircraft. So yeah, so while choosing the airfoil of our aircraft, we mainly need to examine two graphs for selecting our airfoil. And where will we examine those graphs? We will examine those graphs only at the design CL location. And that is the significance of design CL. So first graph which we need to look at while choosing our airfoil is the CMCL graph. So this is how the CMCL graphs for various airfoils look like. And let us think that we have to choose between these two airfoils, this blue one and this yellow one. These two airfoils are available to us, and we have to choose which airfoil will be better for us for our mission requirements. So let us assume that our design CL is around 0.25. That will lie here, right? So if our design CL lie here something, so we will check the graphs at this location only. So what we will do is, looking at this graph, we will go for the airfoil which has a CM value closer to 0 but negative at the design CL. So among these two graphs, we will choose this blue graph. That is the airfoil which has this blue curve. Why will we do that? We need to, as mentioned here, we need the CM value. We select the CM value which is closer to 0 but negative. So why we need it negative? We need it negative for our statically stable. But why do we need it closer to 0? We need it closer to 0 because we don't need excessive movements for small disturbances in our aircraft, right? So if we get very large reactions from our aircraft while it experiences very small disturbances, it will not be a feasible case. So we choose our CM value such that it is negative but closer to 0. That's why uh, so that it provides us appropriate reactions in case of some disturbances. The second graph which we look at is the CL by CD graph, again at the design CL. So yeah, now let us assume that our design CL, let's say, was about 0.8. So here in this graph, what we will do is, we will go for the airfoil which has a higher CL by CD value at the design CL in order to minimize the drag. As it is self-explanatory here, we need to minimize the drag as much as possible for our aircraft. So choosing an airfoil for a particular CL which has a higher CL by CD value, we are inherently choosing an airfoil which will provide us less drag. So if our design CL is approximately 0.8, so among these two airfoils, we will select this yellow curve, the airfoil with the yellow curve, because it has a higher CL by CD value, and thus it will provide us a less drag. Yeah, so now what we have is, so now what we had from the previous webinar on weight iteration, we had the total weight of our aircrafts and as well as the different components. We also got the area of wing and area of tail in the previous slides. Also in the previous webinar, we had discussed about weight of battery, configuration of wing. We also looked at size of fuselage here. And we also looked at the propulsion system in the previous webinar. That is choosing your motors and all those things. We had chosen a motor for our aircraft. And thus we have got almost everything. So now we have all things to jump to the build, and you can actually start building your aircraft depending on all those parameters which we have obtained, and that will yield a fairly stable and fairly good performing aircraft. Yeah, so now we have a quick XFLR5 demo on stability lined up for you, and I request Anjali to take up from here.
Yeah. So in the previous webinar, we are done with the plane designing part. I hope you are able to design a plane by now. Okay. So in this webinar, we will be moving to the stability analysis part. Basically, we need to do some prerequisites for the actual stability. So we'll be doing that today. Firstly, let me share my screen. Is my screen visible?
Oh, it's loading. Yeah. Yeah, it's visible. Yeah,
Yeah. So as I said, we are done with the plane designing part. So we'll move to the prerequisites of the plane designing. So let me open a already designed plane. Yeah. So basically, we'll be discussing the graphs of CL, how CL dependent on CM, and how pitching moment depends on the angle of attack. So by here you can get all the graphs. Yeah. So by pressing T on your keyboard, you will be getting like these two graphs we will be analyzing. So main thing to notice in these two graphs is the negative slope. Um, and that really needs to be. Means these graphs has to be negative for the longitudinal stability. And why is that? Because okay, let's say a condition in which your plane is flying horizontally, and suddenly the wind raises and the nose of your plane goes up, which means the angle of attack of your plane is positive. And as you can see in the graph, the angle of attack is positive. We will be having a pitching moment negative. Means the negative convention of pitching moment represent the nose down of the plane. That's why the plane will remain stable, because as you know, the angle of attack is moving it to the nose up movement, and the pitching moment is doing it nose down. That's why we'll be having a negative slope for this graph. Also, you can see the graph for the lift coefficient and the pitching moment. At zero pitching moment, we have a positive lift, means our plane is quite stable. So what we'll do is basically we will be analyzing our stability on like we will be uh, checking the influence of the center of gravity on this stability on these graphs, and then we'll be analyzing the stability part. So okay, we can, yeah. So how we can change the center of gravity? We'll be doing this. We'll be keeping the speed of our aircraft fixed, let's say be 10. And but the main thing is, in the previous plane designing part, what we will be using is the plane inertia. But now we are not using the plane inertia. We are manually changing the center of gravity value, and then checking the influence of it on the graphs. Okay, let's say we'll keep it 85. I think there is some issue in the Reynolds number. Yeah. So as you can see, if we are changing the changing the center of gravity center of gravity point to the 85 from 70, then it will, like, the pitching moment of the graph is decreasing. Like, it will less negative than before, and the angle of attack is more positive. So the plane will be a little bit less stable than before, because as you know, it will be more nose up and less nose down. Then it will be less stable. Okay, so let's change the center of gravity a bit more. Say it 90. Also, you can, like, just type to keep it safe. Yeah. So you can see that the angle of attack is more positive and the pitching moment is like bit less negative than before. So like we have got so many graphs. What are we all waiting for? We are waiting for the neutral point where the pitching moment will not depend on the center of gravity and will be having a graph which is horizontal to the angle of attack line. Yeah. So this is pretty much horizontal. So like we can just approx it to the given value. Like we keep it 96 and keep it 95.5 as like that. So we call as our neutral point. And now what we'll do is for checking the stability part, uh, we'll be like uh, calculating the static margin due to this neutral point. So, what thing is, we analyze the stability part in terms of the static margin. Let's say we assume the static margin for our plane is 15. Then, okay, first I recall what the static margin is. Static margin is basically the distance between the center of gravity and the neutral point divided by the aerodynamic mean chord. If you don't know the aerodynamic mean chord of your plane, then you can find it from here. Like MAC is 0.230 meter. So this is the aerodynamic mean chord of your plane, and having a 15% static margin and 0.230 aerodynamic mean chord and 0.096 neutral point, you can find the value of the center of gravity of your plane. So it is basically 0.061. So by here, what you can do is you can um, okay, first of all, you can save it. Yeah. So by here you can change the center of gravity to the 0.61, which you have find from the neutral point and the static margin. Yeah, and then you can define an analysis. This time we'll be using the plane inertia because we have changed our center of gravity value to what we have find before. So yeah, let me just highlight this. Yeah. So this is the graph of 15% static margin we have find using the static margin. So this at this static margin, the plane will be highly stable, or we can say more stable from where will be having like center of gravity value. We change these planes. So yeah, at this point the plane will be having more stability compared to these parts. Now so you can like analyze these graphs also by changing the center of gravity, and now you are good to go for the stability analysis part. So yeah, that's all from my side. If you have any doubt, you can ask or unmute yourself.